Okay, well, welcome everybody to Heidelberg for this latest edition of the Joint Astronomical Colloquium. I mean, in the summer, we're complaining about the hot heat, but today this is the coolest place to be to hear about the hottest topic, namely cosmic rays. And we are very, very pleased to welcome Brian Reville from the Max-Planck Institute for Nuclear Physics. In fact, he's the leader of the astrophysical plasma theory group at MPIK, which deals with a whole range of problems associated with the acceleration, propagation of cosmic rays, and also other things associated with these strange particles. So Brian did his PhD at University College Dublin, graduating there in 2007. And his title of thesis then was Magnetic Field Amplification in Collisionary Shocks. He then went to Kernphysics, the same institute as he is now leader of the group, where he was working in particular with John Kirk. John Kirk is here in the audience today on a number of things. I remember relativistic shocks, plasma pulsar magnetospheres, all those great things. And then after that, Brian went to Oxford, where he was working for another 3 years with Tony Bell. And of course, that was all to do with shocks and supernova remnants. But important to note at that point was the laboratory astrophysics dimension, which is something which I think is I've learned myself from Brian, is a very important thing to understand the microscopic properties of plasmas, which you can't really always treat very well as fluids. And then after that, Brian went to Queen's College, Belfast, took a lectureship there, and until he came back to Heidelberg to start the astrophysics plasma theory group in 2019. And then one aspect of this, I think, that Brian has really pushed forward very effectively in that time was the connection between these theory, not just ab initio theory, but modeling theory, and the actual observations in the gamma ray spectrum. And I think Brian is going to tell us something about that connection in his talk today. So without any further ado, thank you, Brian. Take it away.
So, can you hear me? Hear me well, I hope. Thank you very much, Richard, for that very kind introduction. And thank you all for coming. I was afraid that I would scare away the audience. I was warned about this with my complicated title, and it seems it worked. So probably I was told I should explain what the word conundrum means. The conundrum, of course, if you look up the dictionary, it is a problem that is very difficult to solve. It also has a second meaning, which is that it's a question or a riddle, which often has an answer, which is a play on words or a pun. So I had a backup title on how probing PV particle production proves a problem of reduced proportion, but I thought that was just preposterous. Moving on. So I should mention a little bit about my colleagues and what we're doing at MPIK, which is the main focus of this talk, but I'm trying to make it broadly accessible to everyone in the community. So I should highlight here my dear colleagues in the astrophysical plasma theory group, which makes working there so fantastic. And of course, we work very closely with the non-thermal astrophysics division, which is led by Jim Hinton there. And this is a photograph from our recent retreat. I should also point out that, of course, we try to somehow maintain or live up to the legacy that was left behind by the theory division, which was led by Professor Heinrich Volk, who's sitting here also in the audience, and the colleagues that were in his division at the time, so John Kirk, Felix Aharonian, and Richard Dendy, and many others that passed through over the years. They really were one of the leading groups in plasma particle acceleration theory for many decades. Okay, so an outline of the talk. So really just to introduce the cosmic ray origin problem, and I thought I enjoyed very much many of the talks this semester that were presented by Philip and others, and were they touching on historical aspects, and I thought I would have a go at doing something similar. And then I'll talk a little bit about particle acceleration and astrophysics. I'm really going to focus on my area of expertise, which is shock acceleration, so how particles are accelerated very effectively at shocks. I'll present the evidence, theoretical, where we stand on that, why we think it connects to, why we think we're advancing towards a solution to the cosmic ray origin problem, and the key aspects of that, particularly efficiency and maximum energy, which really tie into the observations. And then I will talk a little bit about the work that we've been doing in recent years, some of the big breakthrough discoveries and developments in gamma ray astronomy, which is closely intertwined with this field, and then touch off with some final remarks on massive stellar clusters as a possible source to one of the outstanding problems. Okay, so a not very complete cosmic ray discovery timeline. This is probably some of you heard of this before in your undergraduate physics, but it's nice to refresh. So 1986, Becquerel and Marie Curie, Skłodowska-Curie, again, first discovered radiation, and they thought that the source of all the ionization was from radioactive isotopes that were in the Earth, in rocks. About 1909, Theodor Wolff takes his electrometer up to the top of the Eiffel Tower and realizes that the ionization level, in fact, increases as you go up slightly. Wasn't taken so seriously. So then Victor Hess, in about 1911, decided to make balloon flights and then going up to 5 kilometers above sea level, again with a very advanced electroscope, and then found again that the ionization rate increased steadily as you went up and up and up, more or less confirming that it was a source of ionizing radiation hitting our atmosphere from outside, our not from terrestrial source, and more importantly, by doing it during eclipse, it could confirm that it wasn't coming from the sun, but was really of a cosmic origin. So then in the 1920s, Millikan, which coins the term cosmic rays, pretty much convinced that these were a type of gamma radiation. And here I'll make a little digression because I came across some rather cute articles. So I don't know if this is actual genuine. I found it in somebody else's webpage. And I don't know how you trap a cosmic ray in a little ball like this. But anyway, what I thought amusing was how he found that these rays streamed through the roof and walls of his house with appreciable hindrance. But meanwhile, experimentalists accidentally discovered that the human head absorbs 5% of the cosmic rays that strike it while passing through. And as we all know, some heads are thicker than others, so that number should be taken as an approximation. There was a number of strong claims that Millikan made, and other clever people like Arthur Compton here, living his best life, who disagreed with that. So he said Millikan was quite adamant that these cosmic rays were in fact rays, photons, and the birth cries of atoms being born in interstellar space. Compton made the very sensible observation that there seemed to be an east-west asymmetry, and that the arrival varied with measurements varied with latitude, and therefore they should be charged particles. And there was a time when this made the front page of the New York Times. So on the New Year's Eve, 1932, this was on the front page of the New York Times, and I did check this, and it is true. Okay, so the matter was settled in the 1930s with Skłodowski or Skobelson and others, but primarily by Bruno Rossi and Pierre Auger, who really discovered that these air showers were quite extended by correlations, Geiger counters placed at large separation, more or less confirming that they had to be of a charged particle origin. And of course, then we get to today, where there is a huge global effort to try and understand the energy spectrum and the composition of cosmic rays. Now, I'm not going to focus too much on these experiments, but I just want, because what I'm interested in is understanding where they come from, right? Not how we measure them. Okay, so what are they? So cosmic rays, if you take the measurements, so here are measurements at about a GeV in energy, and they're about 90% protons, about 10% of that is in helium, 10% of that in electrons, and about 10% of that is divided amongst all other antiparticles and other nuclei. And so one question that comes up sometimes by people in our group is, what exactly are cosmic rays? What do we mean when we say cosmic rays? And this term is used quite broadly and often not very precisely. So when we talk of cosmic ray origins, we really mean the ones that are hitting our atmosphere. So where could these be coming from? But they're so pervasive in the galaxy that this word is used in general to describe the non-thermal sea of particles that permeate our galaxy. so what does the spectrum look like? So then this is taken with many different experiments, and we see the spectrum as a function of energy, and quite remarkably extending over more than 10 decades in energy, and covering equal number of decades in flux. They are almost featureless, and the features are very important because they tell us something. They're almost isotropic, which is unfortunate because then it's very difficult to tell where they come from. And they're almost understood. They're always almost understood. Of course, we've known about them for 100 years, but we really are close to understanding where they are coming from. Okay. The key features I want to highlight here are, okay, so we have at the lowest energy ends here, so at about a GeV, these are solar modulated cosmic rays. So that's the solar wind blocking low energy cosmic rays. We have this extended straight region here between this region here and the so-called knee. And the knee then it's hardening. So the knee is at a few peta electron volts. This hardening, which again, still galactic in source. And then at some point it has to transition to extragalactic, simply because the gyro radius of these particles at the highest energies are larger than the scale height of the galaxy. So they must be extragalactic. Okay, so you might think, why should I care about this? And of course you should, because BBC tells you so. So this was an article written a few years ago about how Intel plans to tackle the cosmic ray threat, who's going to kill you and everyone you love. The idea here being that as electronics get smaller and smaller, just a small charge produced in these showers could in fact change a 1 into a 0, and planes would drop out of the sky. So companies have to start worrying about these kind of effects. But another issue, if you look this up, and there's a lot of research on this, is if cosmic rays actually have an impact on climate. And here the idea is basically that the formation of fluorescence in the atmosphere, as these cosmic rays are determining the ionization rate, how these reflect sunlight or trap sunlight, et cetera, et cetera. And so there's an experiment set up at CERN, the cloud experiment, where they try to reproduce atmospheric conditions and study the effect of cosmic rays, how they might impact that. And again, it shouldn't be a surprise that the people at CERN are very interested in cosmic rays, and very knowledgeable of cosmic rays, because of course it is effectively their birthright, or where their history comes from. So I have another little timeline here, which I thought was kind of cute. So this is from the Charm of Strange Quarks and the history of different particle discoveries. So here on the timeline we have Hess makes his balloon voyages, happened to be the same year that Wilson perfected his cloud chambers. And then in about the late 1920s, Skobelson started experimenting with cloud chambers with an external magnetic field and seeing these cosmic ray tracks. He was really able to see. He already had a fairly good idea that these were charged particles back then. And so then we can really see this was the era of the cosmic ray era of particle discovery. And so the next few particles that were discovered, the first few particles that were discovered after the neutron, were in fact discovered in cosmic ray experiments. So here was Anderson discovering the positron in 1933 and the muon in 1936. And I thought I came across this was interesting. There's a very nice book, The Atlas of Typical Cloud Chamber Pictures, written by Gentner and Botha, who were the founding fathers of MPIK. And so there's a long history there as well of cosmic ray research. Okay. So then in 1954, the Bevatron, so particle accelerators, were able to get up to multi-GeV energies. And then the accelerator era truly began, and we know where that led to. But so it's important that these theoretical physicists remember where they come from and not commit some form of matricide. Okay, I don't want to talk about this too much, but it's now become quite popular that cosmic rays, we know, contain a significant energy density of the galaxy. So it's more or less equivalent to the energy density in the magnetic field, and also in starlight, and also thermal motions in the gas. So it stands to reason that it probably has an impact, and including it in a somewhat crude manner in these galaxy scale simulations, you can see that it produces quite a noticeable difference, particularly if you go to low mass galaxies. So here is the hydrogen column density for a Milky Way-like galaxy, so a few 10 to the 10 solar masses. If you go down to slightly smaller solar masses, smaller galaxies rather, then you see a more significant influence. So cosmic rays are almost certainly playing a part. I think this is a field that will develop and something that we will try to also provide better subgrid models for. Okay, so what are the big questions? when we get down to our conundrum. So the biggest one is, of course, where do they come from? And as I mentioned before, because cosmic rays are isotropic to 1 part in 10 to the 3 or more at Earth, then it's very difficult to tell from direct measurements where they come from. And this, of course, makes sense. These particles are charged. The intergalactic magnetic or interstellar magnetic field is highly turbulent. And so the mean free path for a GeV particle is about 1 parsec, extending up maybe at a PeV and about 100 parsec. Okay, so this is increasing with energy. So within 1 parsec or a few parsecs, a particle has forgotten where it's come from. And so they're randomized in the galaxy. And so then an equally important question is, where do they come from? So here I'm being a bit more specific. I'm aware it's the same question. So we want to seek a source model that can account for all of the experimental data. And that means, can we account for the fact that we have a power law extending over multiple decades in energy? Then we have a break. Why is the feature exactly here at a PeV? Why does nature do this? How many subpopulations are there? Where exactly is the transition to extragalactic? Is there just one population for the extragalactic? Are there many sources, many different mechanisms contributing to that? So understanding where they come from is a multifaceted question. And we're still trying to figure out many of these problems. But the first question, where do they come from, was already answered, I think, pretty convincingly already back in the 50s by Vitaly Ginzburg. So this very simple energetic argument, and it goes more or less the following. So we know the composition. We have good experimental measurements of that. And we see that cosmic rays are highly overabundant in certain elements, particularly lithium, beryllium, boron, and some other heavy ones, titanium, etc. And then these are most likely produced in various spallation events. Okay? And so by making these measurements, and we can infer more or less the grammage that has been experienced by these particles. And then it's a very simple calculation. The grammage, then there's the product of the velocity, its wandering time, and the average density that it saw. And the measurements give us about 5 to 10 grams per square centimeter. And so this implies that at least at about a few GeV, these particles are wandering around the galaxy for a few million years. Okay. Then it's a simple estimate to make. We know the local cosmic ray energy density, about 1 electron volt per cubic centimeter. We know the time that it's likely resident in the galaxy, a few million years, and therefore we can work out a total power just by multiplying by the velocity, the volume of the galaxy, and it's about 10 to the 40 ergs per second. So this turns out is about 10% of the kinetic energy input rate from supernova remnants. And so if supernova remnants are able to convert about 10% of their energy of the kinetic energy into energetic particles, into cosmic rays, then we should have sufficient supply to maintain a steady state. Okay, there's very few other objects. In fact, there's no other class of objects that can reliably do this at the same time. Okay, so we've established that supernova remnants are probably the source, but we didn't say how they produce and why they produce power laws. Okay, so how do particles get accelerated in astrophysics? So let's start with how particles can be accelerated in the laboratory. So one way that is commonly used in linear accelerators is to use gaps. So here you take a simple radio frequency linear accelerator. You have an alternating electric field going between these capacitors, and then you have it arranged in phase such that the particle always sees one sign of the electric field, and so the particle is just accelerated linearly as it propagates along this accelerator. The difficulty, of course, in astrophysics is that we don't have devices like this. You can have a very similar process. You can surf on a large amplitude wave, which you can resonate with it. You can produce a similar type of effect. Doesn't always produce power laws, and these type of gaps or these type of structures, while they can occur, for example, in the winds of pulsars, they're not so common. So an alternative was proposed by Enrico Fermi, where he showed that collisions between fast particles and slow-moving clouds can, in fact, also accelerate particles to very high energies. Effectively, the particles are trying to come into thermal equilibrium with macroscopic bodies, and therefore they carry an enormous amount of thermal energy, and therefore particles can accelerate it up, if given enough time, can accelerate up to very, very high energies. The complications with this, of course, is that the process can be quite slow, which Fermi already pointed out, and it doesn't naturally produce power laws. You need to fine tune a little bit. So it took about 3 decades for more, let's say, reliable approach or solution to this that solved all of these problems. And it appeared all at once in the late 70s in these famous 4 papers. And the idea was basically to exploit shocks. Okay, and so shocks are a little bit different than Fermi's random clouds, which were moving effectively chaotically or in random directions. Here, at a shock wave, all of the scattering centers are always converging. So it's always these head-on collisions, and the acceleration can therefore be, in fact, quite rapid. So just to give you a quick overview of the key steps of the process. So particles are somehow selectively lifted from a thermal pool. This is what's called the injection problem. And I'll mention a little bit about that in a second. Particles move upstream. So imagine these particles are moving upstream en masse, very ambient, quiet conditions. They produce electric currents, excite plasma instabilities. So that's, let's say, my favorite area. These instabilities then act to isotropize the particles ahead of the shock. So they're isotropized in the upstream, and therefore the shock is advancing up through this medium. They get overtaken. In the downstream, there's lots of post-shock turbulence. Particles again isotropized again. And in fact, the probability of not returning to the upstream is very small. It's of order u over v. U is the shock velocity, which could be a few thousand kilometers per second, and v is effectively the speed of light. So this is a small number for most supernova remnants. And so steps 2 to 4 repeat until they can't. Okay, so particles, via this process, they increase their momentum by a fraction, delta p over p. So that's their fractional increase of order u over v, which is exactly the increase you would get just bouncing between 2 walls that were approaching each other. And there's a fractional escape, basically determined by this escape probability. And it turns out when you combine these 2 effects, you naturally produce power laws. And in fact, you have to, because by making the observation that you're isotropized on both sides of the shock, there's a completely random process, there's no intrinsic momentum scale in this problem whatsoever. And so the only solution you can have is a power law. Okay? And so it turns out this power law, and why this theory is so beautiful, is that it depends on a single parameter, the strength parameter of the shock, in its simplest form. Okay? And so for a strong shock, this compression ratio is 4, and this turns out to give you an e to the minus 2 spectrum, which, allowing for energy-dependent escape from the galaxy, is within reasonably close to what's required to match the cosmic ray, the observed cosmic ray spectrum. Okay, so the answer is yes, we can produce power laws. We can produce them over a large energy range, and reasonably close to what is the expected for cosmic rays. So I should highlight here, this was showing you that it can produce. Here is a direct simulation where we solved the transport equation. So this is a code written by 2 very clever people here in the room, and called Sapphire++. And so this solves the test particles at the moment for solving how particles move in a plasma. And so what I have here is, here's the upstream region, here's the downstream region, and these are line outs, one in momentum. Momentum is in this direction, and space along this direction. And so if we hit go on this simulation, you can see that particles are injected here at the shock. They start to gradually fill up the upstream and downstream regions, approach the asymptotic steady state solution, which gives you this nice p to the minus 4 power law, or which is an e to the minus 2 power law for relativistic particles. Okay, so the distribution converges nicely, and so approaches the steady state solution. But the question that will be important for determining the maximum energy is, of course, how fast can this proceed? So how fast is the actual acceleration? So we come back to this simple picture, and the acceleration is going to be determined by how quickly or how effectively you can bounce back and forth across the shock each time, gaining a small amount each time. So how many cycles do you do? Okay, so as I mentioned already, particles gain fractional energy gain per cycle. Now I introduced this concept of a diffusive transport. It's familiar from anyone who's done heat transport. So particles effectively diffuse against the flow. So you can imagine in a steady state, you would set up an exponential scale height, which is basically a balance of advection and diffusion. So natural scale length, which is a simple dimensional argument, d over u. And a typical cycle time might be the particles crossing time of that length scale. Okay, so d over uv. And therefore, we can work out an acceleration time. So we have a fractional change in momentum, and we have a cycle time. And we see we get something that scales as the diffusion coefficient over the velocity squared. So if the shock is very fast, the acceleration is very short. If diffusion is very small, then you confine particles close to the shock. Acceleration is very fast. Acceleration time is short. Okay. So here, all the interesting plasma physics is hidden in this diffusion coefficient, yet to be determined. Of course, this requires understanding of the interplay between cosmic rays and magnetic fields. But then the big question we ask ourselves is, can supernova remnants produce cosmic rays up to the knee or even beyond? Okay, so this is the big open question that we're all asking ourselves in the community. The other question I mentioned is that somehow the shocks selectively inject particles. And this is where the era of numerical simulations, particularly kinetic simulations, have really been instructive. So here is a simulation which solves Maxwell's equations together with individual particles. This is particle and cell simulations, and just starts a shock off from nothing, just slamming a plasma into a wall. And you can see that particles are lifted out of the thermal gas and are accelerated up to quite high energies. And it turns out, if you do these for non-relativistic type conditions, it was a relativistic shock, you get two numbers which are more or less consistent with what we need. So on the order of about 10% in terms of energetics. Okay. So these were some work that we did last year and some collaborators in the US. Okay, so let's return to this question on the maximum energy. So we have this number in mind. We want to understand how we can get to the knee. Right? So the knee is a few 10 to the 15 electron volts, and this has been the thorn in the side of theorists for decades. In fact, this was pointed out very shortly after the original papers on shock acceleration theory by Legage and Cesarsky. There was also an independent work by Alan Heavens. And the idea is very simple. You just accelerate. First of all, you have to determine an expression for the acceleration time, which is why I did. And we equate that with the age of the system. That says, okay, that will be a good estimate for the maximum energy. Of course, as I said, we need a model for the diffusion coefficient. So what we'll do is we take the limiting value for magnetized transport. So if you imagine magnetized means particles are doing helical trajectories, which means that the mean free path must be longer than its gyro radius. Yeah, so the time it takes to do part of a helix. So we take the limiting value of that. It's called the Bohm diffusion coefficient, the Bohm diffusion, and that's the mean free path equal to its gyro radius, and this gives this more or less scaling. The diffusion coefficient is the gyro radius times the speed of light. And then we can equate these numbers here, and we find that the maximum energy is determined when the gyro radius is a fraction u over c times the size of the system. So it's not equal to the size of the system, but it's a small fraction of it. Equivalently, we can write this in terms of the maximum energy as being effectively very, very close to the maximum potential across the source. Okay, so UBL is the maximum potential. Okay, so if we actually plug in numbers, this is where the problem comes in, and has been the problem, and is still something of a problem. If you plug in actual numbers relevant for an astrophysical shock, for supernova remnant, naively, you would get the maximum energy is about 100 TeV. So it falls an order of magnitude short of the what's required to explain this feature in the cosmic ray spectrum. So this was pointed out, and it took a very, very long time to come up with solutions. But the solution seems to be, and we're quite confident that this is the case. So these are fixed by observations. The shock velocity, there's nothing you can do. It is what it is. The size of the system is what it is. But the magnetic field doesn't have to be what it is typical of the interstellar magnetic field, but could be in fact much larger. And there's quite a lot of evidence that that is in fact the case. So this was where high resolution X-ray images really revolutionized the field around the turn of the millennium. So the idea here is quite simple. If we have relativistic electrons and we can measure non-thermal synchrotron emission from these relativistic electrons, we know the peak frequency or the critical frequency at which these particles are emitting. So it's at a few keV for these energies or this type of magnetic field. And we also know the cooling rate for these relativistic electrons. These are known. And so the cooling time would be on the order of a few years, again, at these energies, these magnetic fields, which more or less corresponds to what we see. We see inter-year scale variability in the X-ray emission, which implies that the magnetic field here has to be on this order of milligauss, not microgauss. Okay, so this number can be hundreds or more larger than what you would naively expect. And so then you would say, oh, then the problem is solved. You know? We can just plug in a few hundred microgauss here, and we can easily get beyond the knee in the cosmic ray spectrum. Turns out that it's a little bit more complicated than that. And to understand why that's the case, we need to understand how magnetic fields can be amplified at these shocks. So here is where the complicated plasma physics would start, but I'll try to do and as simple as possible. Don't worry. Okay, so the picture that we have is, as I showed you in the simulations, so in the shock rest frame, you can imagine you set up some steady state solution. So we have the downstream was constant, and you have this upstream extended precursor. Now the upstream is now moving in towards the shock, but we could now go into the upstream frame, and now all of these cosmic rays are now moving up through the upstream medium, and they're carrying a very large current. Okay, so they were just a stationary density before. Now they're carrying a current, and if we take large length scales, so we can ignore displacement current associated with small charge separations, and if we assume that the magnetic field is fairly smooth, we see that now the sum of the currents has to be maintained. And so what happens is that as this cosmic rays are drifting through the plasma, the background plasma has to respond. And it responds by compensating this current, which then the electrons are then stuck to these magnetic field lines and produce an uncompensated current. And these drive a very, very fast instability. And it turns out that this is very easy to actually simulate. So you can just throw this into any MHD code. You just have to add an additional term, a driving term in your momentum equation. And what happens is small little loops of magnetic field just gets driven apart by this responding current. And you can see here starts off as just white noise. And then you can see these large coherent structures where the magnetic field is amplified by, it's already amplified by a few. And then it very quickly grows to large scales to the size of your simulation box. And you can amplify the magnetic fields by well over an order of magnitude or more. Okay? So this is fairly straightforward to do. We can make the simulation boxes bigger, and it doesn't really make much difference. Once it gets into the nonlinear stage, it very rapidly grows to large scales, and in principle, would start producing very strong fields and very strong feedback on the cosmic rays. And so this gives us a rather simple way to try and understand how you might be accelerating the highest energy particles. Because now we have a way of producing very, very strong magnetic fields and producing them on length scales where we can really influence the transport of these particles. Okay, so the idea that we proposed is fairly straightforward. So you imagine you have your cosmic rays being accelerated at a shock here, and imagine some region that's very far upstream. So it's quite quiescent, nothing much going on, turbulence is weak, and all these cosmic rays are being accelerated at the shock, and nothing's really confining them. Yeah? Just the low energy ones are confined, the highest energy ones are all zipping out. They start driving this current through the plasma, and as that little plasma element is moving in towards the shock, in the shock frame, the fields get stronger and stronger and stronger and very rapidly grow to larger length scales, and at some point you confine all these particles. Then they get accelerated to higher energies. The higher energy guys, fields are on too short a length scale, they zip upstream, and then they repeat this process in a self-similar fashion. So we can play around with the numbers. A very simple way of doing it is determining the current is a certain fraction of the energy flux processed by the shock, and it's all concentrated in the maximum energy particles, maximum energy cosmic rays. And then if you throw that into the plasma instabilities, which we have an analytic theory for, you can work out the maximum energy. And so it turns out that the maximum energy looks remarkably similar. It's about 100 TeV, but of course you can play around with these numbers. So there is a little bit of variability. So the first thing you might not notice is that here the magnetic field no longer appears. So the magnetic field is not appearing in this equation, although it did in the previous ones. But we also have a very strong dependence on the shock velocity. So a slightly faster shock in a slightly denser medium might, in principle, be able to accelerate up to much higher energies. So one possibility, and what we think is the most likely possibility, is where we get these densest environments is in just around core collapse supernova remnants, where you have a very dense wind, and then we can just replace the density here by the mass loss rate, and we find a maximum energy, which again, for quite high mass loss rates and quite slow winds, will be mildly supersonic, can get up to about a PeV. Okay, so we can take stock at this point before we discuss observations. So I think from a theoretical perspective, we have a strong energetic argument in favor of supernova as primary cosmic ray source. This was Ginzburg's argument back in the 1950s. We have a process that produces power laws over a very large energy range, which is shock acceleration, again, known since the late 70s. Now, numerical simulations in the last decade or so have really demonstrated that this process can be efficient, can start, it's self-injecting, and can amplify these magnetic fields. And we have a way to get close to about a PeV if conditions are right. And this is somehow comforting, right? Because if it was easy to get to a PeV, that's the argument I like to make, if it were easy to get to a PeV, then you'd be curious why there was a knee at the PeV. So the fact that there is this feature appearing there should imply that it is an intrinsic limitation of the majority of accelerators in the galaxy. Okay, so how do we test this theory with gamma rays? Okay, so a little digression into gamma ray measurements. So we can do this by a number of ways. One is to measure gamma rays directly using satellites. So this is the Fermi satellite. Or we can observe them indirectly, looking at their products. So when the gamma ray hits the upper atmosphere, that produces an air shower, which puts a shower of Cherenkov light, which can be detected with imaging atmospheric Cherenkov telescopes. Or you can measure the air shower directly with high altitude water tanks. So the Cherenkov's detectors operate like this. They see directly the air shower, and they can take multiple with stereoscopic imaging. They can take multiple of these, I would say, these ellipses here, and redetermine the direction in which the gamma ray arrived from. Or with these water tanks, using the delay in the arrival niche detector, in principle, can reconstruct the direction which the gamma ray came in. Okay, so these are the two ground-based methods for detecting gamma rays, and space-based. So just to focus a little bit on the ground-based, because this is where I'm more interested in, and particularly for looking at higher energies. So again, they fall into these two categories. These are these high altitude water Cherenkov detectors. So the Lhasa Observatory in China, in the Sichuan province, and then the Hawk Observatory in Mexico. And then there are the three leading current imaging atmospheric Cherenkov telescope experiments, Veritas in the US, HESS in Namibia, and MAGIC in La Palma. And then there are the two future instruments or observatories. One is the CTA, which will have a northern and a southern site, which is a scaled up version of what was done in these experiments. And then there is SWGO, which will be a similar observatory, something between these two. The final design is not fixed, and will be in the southern hemisphere. So I should highlight here that MPIK has a lot of involvement in these four instruments, in Hawk, HESS, CTA, and SWGO, and MPIK has a very long history, as do Landessternwarte and other places at Heidelberg, with HESS in terms of its construction and its continued operations. Okay, so just to give you an idea, this is not what SWGO is. This is a simulation tank that's up at Max-Planck. It will actually be a much bigger, ambitious project. Again, the final design might look something like this, might be in a lake, to be decided soon. And what it will do is basically monitor the entire southern hemisphere, so this part of the sky here, which will give it a large view of the galactic plane, where there are many interesting sources. So I think it's important that people know these very exciting activities that are going on here in Heidelberg. And reach out to us if you're interested. Okay, so what does the galactic gamma ray sky look like? So some of you are more familiar with optical or surveys or similar here. Gamma rays might look a little bit different. The first thing that stands out, similar to everything, that most of the sources are all concentrated in the galactic plane. Here, this is primarily because we know there's a sea of cosmic rays that's colliding with all the gas in the galactic plane. So you have protons or other nuclei colliding with protons or other nuclei, producing pions, and neutral pions can decay into gamma rays. which is primarily what we're seeing here. But of course, there's also lots of individual sources. And this can be produced by pp interactions, so proton-proton collisions in the sources, or they could be electrons producing inverse Compton by scattering ambient light, nearby light. And just to highlight some interesting sources that you might be detecting. So this is a supernova. This was the image that was on my first slide. This is Oryx J1713. It's our basically the quintessential gamma ray supernova. Then there are other interesting sources like SS433. So this is a microquasar with a black hole at the center shooting out two very fast jets, detected up to very high energies. And then more extreme objects like the Crab pulsar, which has a spectrum which is extending all the way up above a PeV. So photon energy is above a beta electron volt. Okay, so but I want to focus on supernova remnants. This is the main focus of the talk because its connection to cosmic rays. And so here is a collection of all observed, directly observed supernova remnants. And so the key point that I wanted to make here is in an inelastic collision between cosmic ray proton and an interstellar medium particle, about 10% of the energy of the cosmic ray is carried away by the gamma ray. Okay, so when you see the photon energy here, to multiply by 10 to get it roughly to get the equivalent cosmic ray energy, and you can see that none of these supernova remnants seem to be really getting much beyond maybe 10 to the 14 or 100 TeV. Okay. So there's no evidence currently of ongoing PeV acceleration in a supernova remnant yet. And so the question is, are they too old? Right? The argument that I made in the previous slides was that we think core collapse supernova remnants have the right conditions for producing PeV cosmic rays, but they should be doing it when they're very fast and very young. And so if they slow down, then it shouldn't have such efficient acceleration or such high energies anymore. And so the question is then, do we simply need to wait for another core collapse supernova remnant to go off nearby? And I would say no. Why would we wait for that? We can still test our theory. Okay, so this was a little bit of serendipitous fortune. Perhaps you know what novae are. So novae are binary systems with a star around a white dwarf companion. And so what's happening is the white dwarf is eating material or secreting off the companion star, and it accumulates material on the surface for a certain time until it reaches a critical density and temperature, and then a thermonuclear explosion occurs, which launches a shock wave basically into the surrounding medium. Now, for a certain class of these novae, particularly what are called recurrent novae, they typically have a very massive star which is accreting at quite a high rate, and they produce these novae quite frequently. And one such example is what's called Orisophyuki, which is a recurrent novae which goes off roughly every 15 years. And so it's known that it's a white dwarf with a red giant companion, and it underwent an outburst in August 8th, 2021, and we were there on hand with Hess to observe this event. Okay. Now, the previous event was known to have produced shocks at several thousand kilometers per second. So it's got a shock that's moving at several thousand kilometers per second. It has a reasonably high mass loss rate from the companion star, and obviously not from the white dwarf, and the winds are usually quite slow. So these are typical red giant wind parameters, supergiant. So the theory that we were applying to core collapse supernova remnants, in principle, we could apply the same argument to this nova. Okay, so rather than the shock going off into its own wind, here we have an explosion on the surface of the white dwarf and launching a shock into the wind of the red giant. And so if we plug in the numbers into our previous formula, we find that the maximum energy, again, for these types of mass loss rates and wind velocities, would get you on the order of several TeV. And so again, if you were to produce, if they're colliding with dense material, producing gamma rays, you would expect them to be producing TeV photons. And this is exactly what we saw with Hess. Okay, so on the sixth night here, we had a very significant detection of photons reaching up close to, or basically at a TeV. Okay, so this lends some confidence that the model that we're applying is right. And I should highlight that there's no way you could get this energy with a simple Parker wind type solution. You would have to have this strong magnetic field. So magnetic field amplification was a key part of this, this prediction. And so a big question is, does this really scale to, if we scale up these numbers to supernova remnant type parameters, are PeV still possible? And of course, again, you need to have a very, very high mass loss rate and quite a slow wind. Okay, so a question is, should we be thinking of alternatives to supernova remnants? Some clues towards this have been starting to emerge, particularly with LHAASO. So LHAASO has an instrument has sensitivity extending up beyond PeV, and so it's detected multiple sources with photons extending above PeV. And one particular source of interest is the Cygnus region, where they have now released only a few weeks ago their spectrum, which extends again above PeV. And again, the arrival of these photons is somewhat correlated with the star-forming region Cygnus OB2. So are star-forming regions then a possible alternative? And if so, what could be going on there? So here is some star-forming regions, OR136 in the Large Magnetic Cloud, Westland 2, Westland 1. And this is particularly interesting because Westland 1 was recently detected by Hess. And it's, well, it was detected long ago, but it had this new beautiful map, which is telling us something about the geometry. And so the standard model that people have for these star-forming or these superbubbles is that you have some compact star-forming region in the center, many winds acting together, driving a collective wind, which then shock at some wind termination shock. You have the shocked region, and then the whole thing is expanding a bubble into the external medium. And so the question that we have in mind is, where can you accelerate? So to get an idea of how that simple spherical cow model works, our group here has been doing lots of very nice simulations, 3D hydro and MHD simulations using the Pluto code. And so if this works, there we go. So you can see this is, I can't remember how many stars are at the center of this one. 10, okay. So there's 10 powerful stars here at the center, all concentrated in less than a parsec. And you can see the winds colliding, forming a large-scale collective wind at some point. And the thing is that you should hope that this is in some way reminiscent to what you're seeing here. So you have, again, like in Westland 1, you have many, many stars within this one parsec region here. And we see this large bubble structure at about 10 or more parsecs, which could in some way correlate with that structure that was there. Okay. That's not way there. Okay, so the question that we asked ourselves again was, what are the possible acceleration sites that could be occurring here? So what could supernova remnants be doing, or what could superbubbles rather be doing that individual supernovae cannot? And so Thibault was put to task on this and considered all possibilities. So we've got many shocks. There's one out here. It's too slow. It's not going to get you much. You could have a supernova, just a random supernova going off in the superbubble. It's very low density. Might get up to a PV if conditions are right. You have the collective wind termination shock, which again, we have hints that it could be an interesting site for acceleration. But even most optimistically, it's only going to get up to maybe a few PeV in the most optimistic scenario. You could have classic second order Fermi in the bubble of the superbubble. And again, this is probably not going to get you more than a few hundred TeV. But there's one clearly preferred candidate, and this is a supernova that's embedded in the wind termination shock. So this is a supernova going off in the core. And the reason that this might be more favorable is that, firstly, we believe that this region in the core could have a highly turbulent amplified magnetic field. So the fields here could be on the order of 100 microgauss or more. And in principle, this is where most of these massive stars are occurring, which can produce very strong core collapse supernova remnants with very fast shocks. This was just to highlight that indeed MHD simulations also show that fields on the order of 100 microgauss are indeed achievable. Okay, so if you can produce very fast shock in these very strong fields, then it's not so much that it's like the previous case where you have these core collapse supernova remnants in the dense medium amplifying magnetic fields significantly, but you have these very fast shocks occurring in a very special environment, the special environment being provided in the cores of these massive stellar clusters. Okay, so it requires these clusters to be young and compact so that you can concentrate this energy in the central region and get these strong magnetic fields. And of course, it needs to be young because you want these strong winds, and you want big, fast shocks. Okay, so Thibault then did some very nice work where he extended beyond this, where he took some latest catalogs, Gaia catalogs, and where people had collected the details of all nearby clusters, and made very nice work where he established about 16% of the clusters, at least in the nearby sample, are young and compact. And from this was able to establish a model in which you could work out more or less how many core collapse supernova remnants could be going off in special conditions that we needed to get beyond PeV for protons, and then heavier elements getting up to slightly higher energies. And so putting all these together got a very, very nice fit to basically all existing data. And so here we see the existing data. We see it composed of basically 4 different contributions. One is sort of your standard supernovae. These are ones that are not going off in compact clusters, rather canonical conditions. And so you're getting your maximum energy maybe up to a few hundred TeV or more and cutting off here. Then you get this second contribution coming from the collective wind termination shocks, this yellow line, which makes a small contribution. But the dominant contribution is from this red line here, which is the contribution that's coming from these supernovae that's going off in these very dense compact young clusters. Okay. So in principle, these then, and then they meet with the extragalactic component, which was just added on. Okay, and so when you sum them all up, you get quite a nice fit to all the data. Okay, so I think that kind of wanted to wind up on that point. Of course, this is currently still a model, and the gamma ray observatories are still needed to really validate and trying to see if we can see these. So we're really trying to understand all the different gamma ray producing mechanisms in these massive stellar clusters, but they mightn't be the only game in town. And so one other very interesting example is mentioned to earlier, which is SS433. This is this binary system. So microquasar, where there's a black hole and a star here at the center. So right at this dot here, this is a radio image showing the precessing jet, this infamous or famous iconic image of this precessing jet in the inner region, again on very, very sub-parsec scales. But on larger scales, as we zoom out, this is about 200 parsecs across. And this is the Manatee Nebula. And you see these X-ray jets here with their white contour lines. And then these hotspots here, these are the TeV gamma rays. Okay, so these are the low energy gamma rays, and these are the high energy gamma rays. And what this seems to be revealing is that these jets somehow produce an acceleration site out here, because these are electrons that don't get very far. They cool very rapidly, so they don't get very far from the acceleration site. And so there are 2 acceleration sites here and here where these shocks are occurring, and they seem to be accelerating particles up to multi-hundred TeV energies. Okay, so it seems to be one of the most effective detected, where we've pinpointed the precise location of one of the most effective accelerators in our galaxy. And this really was unexpected. And so this was presented by Laura at the ICRC recently in Nagoya on behalf of the HES collaboration. But this is also giving us some insight into what might be happening elsewhere in the universe. And one thing that we're thinking is that the same process, in principle, where we have something like a recollimation shock, could be operating in other extragalactic jets. And if you have a similar type of efficiency, one might naively expect that this may be able to, if it scales up, can somehow account for the highest energy cosmic rays that we know occur. So these extragalactic cosmic rays above 10 to the 20 electron volts. Okay, so I think I can conclude here. So what I wanted to really get across was that cosmic rays play a very influential role across many branches of physics. It's given us a lot, the birth of basically particle physics, discovery of antiparticles, and a lot of the first few standard particles were discovered in cosmic rays. I think the theoretical efforts that were made by people over the years, which I try to present, were fundamental in understanding how particles radiate in other wave bands, which developed the field of radio astronomy, the field of X-ray astronomy, non-thermal X-rays, and related neutrino astronomy, et cetera, et cetera. I mean, it's a major driving force of modern astroparticle physics to try and answer this question. I hope I've convinced you that shock acceleration theory is a convincing mechanism, and how gamma ray astronomy is really focusing in and pinpointing the future direction and try to answer these key problems. And in particular, the next generation of instruments, CTA and SWGO, which Heidelberg has major involvement in, will be able to crack many of these problems in the near future. Thank you.
Thanks so much. That was a really incisive, really up-to-date summary of the situation. You can't get more close to the cutting edge, I don't think, than that. So please, we have time for a few questions, I think, still. So please raise your hands. So Philip Podsiadlowski.
First, can you repeat again why you wanted the mass loss in the progenitors of the core collapse supernovae? And then for how long before the explosion did you need it?
Okay, so we applied really the most simple model. So we were assuming completely steady mass loss rate. It's a standard stellar wind solution, so mass conservation with steady mass loss rate. The reason that you want the high density, because that determines effectively the growth rate of the instability, and so how much matter you process. And so denser environments is generally better. So then the instabilities are more virulent, then you get.
But for how long before did you need it? I mean, you said in the current remnants you don't see anymore the acceleration.
So this is more probably the issue of that you also need the shock to be very fast. So if you're going into a very dense environment, then the shock presumably at some point starts to decelerate. So you need the shocks to be fast, about 10,000 kilometers per second, and you need this wind extending out. Yeah, I mean, if it goes through any change, then we would need to adapt the theory. We haven't done that yet.
I'm just asking because I think there's a lot of evidence that there's enhanced mass loss, but not for 10,000 years, but perhaps for 100 or 1,000 years.
Yeah,
before.
so we believe that the acceleration to the highest energies should be happening in the first decade or so. Decade or decades.
That's your acceleration, but that's then translated into the last 1,000 years of the progenitor.
It depends on the wind of the wind speed, but yeah. So wherever it propagates in a decade or so, fraction of a parsec, yeah.
Okay, another question? Yep.
Thanks for the great overview, Brian. I have a question about the shock and the magnetic field in there. You told us about the acceleration and that you get strong magnetic fields there. But can you comment also on the orientation? So to what degree is that field in the shock turbulent enough that you don't worry about the orientation, or is there coherent structures on large enough scale so that we also have to worry about the orientation? Because the diffusion would be highly anisotropic.
Yeah. Yep. That's a very good question. And this is actually one of, let's say, one of the big open questions which people have really overlooked. So what I mentioned this, and I didn't want to get too much into the details. So to accelerate particles or to scatter particles effectively, you kind of want to have the field disordered on the scale of the particles gyrates. Because this is a highly magnetized concept that particles are simply doing this. But you kind of want, let's say, in the average field, the magnetic field structure should be comparable to the gyrates of the particle. Now, the holy grail has been for the last 20 or 30 years, because of this Legage-Cesarski argument, has been how do we get to the highest energies? And therefore, you intrinsically want to get a lot of energy in the magnetic field on the scale of the highest energy particles. And you need this to be quite flat. Yeah, you need almost so Bohm type diffusion needs almost equal energy per decade in the turbines. And if that's true, then you would expect the field to be highly structured for the lower energy particles. And therefore, deviations from standard diffusion theory probably hold. Particles will be stuck on highly anomalous trajectories. They'll see quite quite structured fields which will dominate the transport. It'll even go beyond anisotropic diffusion, but they'll actually be non-diffusive behavior. And that's part of the reasons why we're developing this Sapphire code, was to really go beyond the diffusion approximation. So if the accelerate, we know that you need to amplify magnetic fields to well above background levels. So therefore, if it was truly turbulent, then there would be effectively no preferred direction. So it will be isotropic. This does not seem to be supported by the latest X-ray observations of supernova remnants, which actually show a reasonably high degree of polarization. It varies from supernova to supernova remnant, but it's not negligible. So there are then questions of whether there is additional, again, they're averaging over quite large beam. And so then there is questions on whether when these structures in the upstream pass through the shock, whether they get stretched and sheared. And then that might lead to a preferential radial direction, which also seems to be what was seen for quite some time in radio observations. A lot of these and the recent IXP observations, that you see this preferential radial polarization in all these supernova remnants, which is a bit weird because you don't expect them to be going off in magnetic monopoles or even split monopoles, right? So they should be going off in highly random fields. And so it does seem that the downstream is being stretched as it passes through the shock. So it's difficult to say at this moment. It requires a combination of more simulation theoretical efforts and observations.
Okay, a question from Christian Fent.
The energy spectrum that spans over a long, over many orders of magnitude. So do you see a time evolution of this? I mean, there are not so many supernovae in the galaxy, you observe. So if there's something going on, you should see some change in the spectrum of this cosmic ray.
Of the cosmic ray spectrum?
The cosmic ray spectrum, yeah.
I don't think there's any evidence of, I mean, only at the lowest energies that there's anything, any evidence that there's variability due to the solar activity. But above the solar modulation energies, there's no evidence that there's any appreciable variability in that at all. The timescales are for any kind of change will be very, very long, right? Because you're the only I mean, if you take we know a rough idea of what there might be a sort of spatial gradient of this, and so then that you can correlate that into a time, and it's millennia.
Fabian has a question.
Actually, many. Extremely exciting talk. Thanks, Brian. So let me start with maybe one of the first questions. I was thinking about all the different energetic processes that might actually produce strong shocks and maybe give rise even to extragalactic stuff. So can you maybe just tell us something about, for example, gamma ray bursts, superluminous supernovae, interacting supernovae, and all this stuff, where you probably have a shock that runs into some medium and so on. What kind of cosmic rays would you expect to get from that?
Okay, so gamma ray bursts are probably, so you have two types of shocks in the gamma ray burst. One is the external shock and one is internal shocks. The external shocks are probably not powerful enough. We use a similar type of Hillis argument. Is not really going to be strong enough to produce the highest energy cosmic rays. They should be getting up to several, well above a PeV, but not up to the highest energy that you can achieve. The internal shocks then, of course, are possibly more favorable because they're highly magnetized, highly relativistic. And so one of my students is working towards this. Here, of course, the problem is that these are, as this Time magazine has told us, the brightest events in the universe. And so there's a lot of photons around. And so P-gamma interactions are quite critical. So generating the highest energy cosmic rays in gamma ray bursts is really challenging. So I would be more inclined to think that it is jets on the shocks that are in jets on much larger scales. There are other possibilities. Again, these large structure scale shocks, they're very slow, they have their own problems. We're also considering other alternatives that it mightn't be shocks at all, but it could be alternative processes like shear acceleration. So when you have these jets, you can behave very similar to shock acceleration by simply crossing in and out of a shear layer. It's more or less the same process. There's some subtle differences, but it's another possibility. For producing, again, you can take those numbers. I mean, the numbers that I presented here I mean, you can apply those to any supernova remnant, and then you can scale up some of the numbers a little bit for these hypernovae, whatnot. You're not going to get much further. Then for colliding winds, it's usually the size is the limitation. So when you have these colliding wind shocks, usually they're quite compact. So we have cases where we do detect very high energy particles. So Eta Carina, again, there's no evidence for particles going much beyond a few tens of TeV, and that's usually it's interesting. For one, it's the only source we know of in the galaxy where on one of the shocks the limitation is probably PP interactions. So it's actually so dense that PP interactions prevent you from accelerating up to very high energies. But on the other side, where we have this slower density, faster wind, then it's the size limitation that kills you. And so Hillis, what we call the Hillis limit, is the one that usually comes in. So you can play this game. Take the magnetic field, take the size, take the velocity, and try to work out what your maximum energy is. And it's usually pretty reliable. Did I miss anything?
Yes. Well, thank you very much. I think that just shows a huge range of questions that maybe can be discussed over a drink. So once again, Brian, thank you very much for this very, very interesting, insightful, and very optimistic talk that we're finally, after 130 years, 20, depending when CTA, etc., comes online, it will finally be solved. And you'll maybe come back and tell us exactly what the solution is at that point. Thank you, Brian.